So in example 2, we're going to solve this trig equation cosine of x plus sine of x times tangent of x equals 2. And when we look at our trig identity hexagon, because this is a product, this sine of x times tangent of x, we're tempted to say that that is a product identity. But remember, product identities, they have to form a hinge, right? Like this one, where the cosine of x points toward the center of the hinge along with cosecant of x, right, where their product is cotangent of x. That doesn't happen here with sine and tangent because there is no vertex in between them for them to form a product identity. So be real careful when you see products. Don't assume that there's a product identity there that you can substitute directly. So instead, we're going to think about the strategy where we change everything to sines and cosines in verifying trig identities. So tangent, I could rewrite as sine divided by cosine because quotient identities make consecutive vertices. So tangent is the ratio of sine over its next consecutive vertex, which is cosine. So I'll rewrite this using that quotient identity as cosine of x plus sine of x. Better fix that before I confuse somebody. So cosine of x plus sine of x times, and now we'll apply that quotient identity to tangent that said that tangent is equal to the sine of x divided by the cosine of x. And that equation is still equal to 2. So that was applying a quotient identity. Now when we simplify, we'll have cosine of x plus, and then sine times sine is sine squared x over cosine of x equals 2. And to add these two terms together, we would need a least common denominator. So to get that least common denominator to match this fraction, which is cosine of x, I'm going to multiply this fraction by cosine of x in the numerator and cosine of x in the denominator, because that way I don't change the value of anything, because a number divided by itself is 1, and 1 times anything is what you started with. So simplifying now, I will have cosine times cosine, which is cosine squared x divided by cosine of x as my first term, sine squared x divided by cosine of x in my second term, and that's equal to 2. So now that my fractions have common denominators, I can add those fractions by adding my numerators together and putting that over the same common denominator. And that's going to be a sine squared x plus cosine squared x divided by cosine of x equals 2. Right, all I did was rearrange those terms in the numerator, put the sine first and then the cosine second, using the commutative property of addition. And the reason I did that was to jog our memory that sine squared x plus cosine squared x, that's a Pythagorean identity. So if you recall our Pythagorean identities in the hexagon, they form these triangles at the top and then the two sides here. So our Pythagorean identities are tangent squared x plus 1 equals secant squared x, 1 plus cotangent squared x equals cosecant squared x, and then the one that we're going to use here in the numerator, sine squared x plus cosine squared x equals 1. So that Pythagorean identity I'm going to apply, and I'll have 1 divided by cosine of x equals 2. So now I've got cosine of x. I can set up this proportion and cross multiply, and I can say that 2 times the cosine of x now is equal to 1. And dividing both sides by 2, cosine of x is equal to 1/2. So to undo the cosine function, we need to take the inverse of both sides. So x by itself is equal to the arc cosine of 1/2. That's the inverse cosine of 1/2. And that means we want to find the angle in the unit circle that has a cosine value. Remember, cosine is the x coordinate. Cosine comma sine is your ordered pair. They go in alphabetical order, so C comes before S, X comes before Y. So to find the cosine, we want to find the X coordinate of the angle on the unit circle where it's a 1/2. So as I look in my first quadrant here, this pi over 6 has a y coordinate of 1/2, but cosine is the x coordinate, so that won't work. And I keep looking, and here at pi over 3, right, the x coordinate is 1/2, and that means that pi over 3 is a solution because it has a x coordinate of positive 1/2. Now there are other quadrants though that we need to consider. So if we recall that acronym, all students take calculus, right? A in the first quadrant reminds us that all 6 trig functions are positive in quadrant 1. The S reminds us that sine and its reciprocal cosecant are positive in quadrant 2. The T tells us that tangent and its reciprocal cotangent, they are positive in quadrant 3. And then the C reminds us that cosine and its reciprocal secant are positive in quadrant 4. Since we're looking for a cosine with a positive 1/2, that means we have answers in quadrant 1 and in quadrant 4. Our quadrant 1 angle we already found. That was pi over 3. So we want to use reference angles now to get that fourth quadrant answer that has the same distance from the x-axis as pi over 3. So since there are 2 pi radians in the whole circle, and my denominator is 3, one lap around the circle would make this angle here along the positive x-axis 6 pi over 3, because that reduces to 2 pi, and one lap around the circle is 2 pi. So if I go pi over 3 backwards, right, in the clockwise direction into the fourth quadrant, that means I'm subtracting pi over 3 from 6 pi over 3 to get an answer of 5 pi over 3. So that would be my second solution. X equals 5 pi over 3. Okay, now to check those answers, we're going to use the graphing calculator, and we want to make sure that it is in Radian mode. So we'll go ahead and turn it on and check Radian mode. Let's see if I can turn that light on and make that a little brighter. So mode, and we're in radians, which is perfect. We'll clear this out. So we want to store this pi over 3 value, so pi over 3, and then see if I can move this up a little bit so you can see all the buttons. There we go. Oh, I don't know if that was better or not. Let's see. Can we see all the buttons now? I think so. So pi over 3, and then the store button is right here above the on. So pi over 3, store, and then x, enter. And now that the calculator knows that we want x to be exactly pi over 3, we can type in this original equation, including the equal sign, to check. So cosine of x plus sine of x times tangent of x. And to get the equal sign, you press second and then the math button, and that opens up the test menu, and number 1 up here is your equals. And we want to see if that equals 2. Now when we press enter, we're asking the calculator a question, right? Is this a true statement or not, when it substitutes in pi over 3 for the x? And if we get back a 1, that means yes, it's true. If we get back a 0, then no, that's not a true statement. So we press enter and we get a 1, and so we know that pi over 3 checks. Okay, now we want to check our other solution of 5 pi over 3. So we type 5 pi over 3, then store x, enter. And instead of retyping that whole equation, we're just going to arrow up to it and press enter, and then press enter again, and we get a 1 again, which means that 5 pi over 3 also checks as a solution to this equation.